Okay, for today's notes, we are going to look at a few more related rate problems, and then you'll have some to try on your own today. We're given this picture here, and it says to find the rate of change in the angle of elevation of the camera shown in the figure at 10 seconds after liftoff. So, what we're trying to find is the rate of change of the angle. So you can see there in the picture that you have this angle theta right here. So we are looking for d theta dt. And so it tells us here in the situation, a television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50t squared. Where S is measured in feet and T is measured in seconds, the camera is 2,000 feet from the launch pad. So we need to find the rate at which the angle needs to be changing after 10 seconds. So if we look at this situation, we could use trig to relate these variables that we have right here, and we would have this equation that they give to us, tangent of theta equals S over 2,000. So that's where we're starting from. And I am going to write this like this. Instead of writing S over 2,000, I'm going to write 1 over 2,000 times S. That's just going to make our derivative a little bit easier to take. So we are going to take the derivative of both sides here. So when we take the derivative of tangent, we're going to get secant squared theta, and we must put a d theta dt here with that. And then the derivative of 1 over 2,000 s is just 1 over 2,000, but we must put a ds dt with that. So this is our derivative that we have here. And now we need to plug in the information that we know. Now here's the problem that we run into here is that they tell us that we're looking at 10 seconds. So our time is at 10 seconds. When we look at this equation, there is no 10 seconds. There's no seconds for you to put this in. That S right there is this length. That's not seconds. But we do have right here our equation S equals 50t squared. So that's what we're going to use to figure out what S is at these given times. So we've got first to just figure out what S is whenever t is 10. So we're just going to plug into that equation. So S equals 50 times 10 squared. And so 50 times 10 squared is going to give us 5,000. So that is the length of S at this time. So we actually don't need that to plug into our derivative, but we need it to be able to find our angle that we need to plug in for theta. So if we take this 5,000 right here and plug it in for S in our original equation, then we can find the theta that we need. So we are going to have tangent of theta equals 1 over 2,000 times 5,000. So that is just going to be tangent of theta equals 5,000 over 2,000, or 5 halves, or 2.5. And so if we do inverse tangent here, inverse tangent of 5 halves is going to give us negative 0.747. Let's see. I'm not sure. That is in radians. It does not tell us whether we need to use radians or degrees here. I'm going to stick with radians just because everything on the AP exam is going to be radians every time. It might be interesting to look at this with degrees, but we're not going to do that for this particular problem. So that is in radians. So that is a number that we can plug in. And the last thing that we need, we've now got our theta that we can plug into this equation. We also need ds dt. And we have an equation for s. S equals 50t squared. So we can take the derivative of this to get ds dt, which is going to be 100t. And then for this particular one, we don't have to put the derivative there, the dt dt, because that would just be 1. Because we are taking the derivative of this with respect to time, which is your variable over here. So if we want to know ds dt at this particular time, we just plug in 10. So we'll have 100 times 10, and we'll get 1,000. So now we have all the pieces that we need to plug back into that derivative equation. So we're going to have, here we'll have secant squared of negative 0.747. Keep that whole number in your calculator. Equals, let's see, what was it? 1 over 2,000 times ds dt, which is 1,000. So we've got secant squared of negative, I forgot my d theta, dt of negative 0.0747 d theta dt equals, this is just going to be 1/2 over here on that right hand side. And in your calculator, you're not going to be able to find secant. So what you can do here is just you're going to type into your calculator 1 over cosine of negative 0.747. And I would do that first, hit enter, and then square what you get there. So 1 over cosine of that number that we have there. That's going to give you, just doing 1 over cosine of negative 0.747 is going to give you 1.36293, and you're going to raise that to the second power. So this is 1.85757 d theta dt equals 1/2. So now you will divide. And so our d theta dt at this point is going to be 0.269, and this is the angle measured in radians, and I believe this is per second for this one. So this would be our answer for this problem. All right, let's try another one. In the engine shown in figure 2.36, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 2,000 revolutions per minute. Find the velocity of the piston when theta equals pi over 3. So I think this is a pretty interesting application. And you may want to go look up a 4-stroke engine or 4-stroke piston operating in slow motion, so you can kind of see what's happening here. So this crankshaft is going to rotate around and around, and that pulls the piston down and then up and down and up and down and up and so on. So it's kind of interesting to see. So you can see here the crank. Let's see, hold on. Let me see if I'm calling it the right thing. I get mixed up on this. Connecting rod is this 7-inch segment right here that we find right here on the piston. And then we have the crankshaft, which is this that goes around and around here. And so we end up with a triangle here, but it's not a right triangle. And since it's not a right triangle, we're either going to have to use law of sines or cosines here. In this particular case, let's see, we're wanting to know about x. So, let's see, this one, we're going to need law of cosines for this one. So, and I'm ruling out law of sines because we want to know about x right here, and we don't know the angle across from x. We actually don't know this angle either, but we can't find this angle. So we're going to use law of cosines. And so law of cosines is going to be, we know this angle right here. So if you remember the law of cosines, it looks like this: a squared equals b squared plus c squared minus 2bc cosine of a. So in this particular case, we are going to let this theta right here be our a. And so that would make the 7 our lowercase a. So we're going to have 7 squared equals, and then b, I'm going to let it be 3 squared. The c, I don't know. I'm going to call it my x. And it's going to be minus 2 times 3x cosine of theta. So if we simplify that a little bit, we've got 49 equals 9 plus x squared minus 6x cosine of theta. And let's go back up and look at the problem and see what they're asking us for here. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the piston when theta equals pi over 3. So we've got this 200 revolutions per minute. We're going to have to do something with that, but I'm going to come back to it because it's the hardest part. We're going to find velocity of the piston. Velocity is your rate of change of the piston. So the piston is right here at the end of your connecting rod, and so it's going to be moving up and down and up and down. So what you're looking for is you're looking to see basically how fast this dot right here is moving up or down or up or down. And so we're looking for dx dt, or yes, dx dt here. That's what we're looking for. They tell us pretty straightforwardly that theta equals pi over 3 here. And so let's go back to this crankshaft rotating. So the crankshaft rotates at a constant rate of 200 revolutions per minute. Well, that's how fast d theta, that's our d theta dt, but it's given to us in revolutions per minute. It's not given in radians. So if we think about what is happening here, if we've got 200 revolutions per minute, each one of those revolutions is a complete trip around the whole circle. So for radians, that would be 2 pi radians. So if we multiply this by 2 pi, then we're going to get 600 pi radians per minute. Okay, so that would be our d theta dt. So we're just going to go ahead and take our derivative here. Derivative of 49 is 0. Derivative of 9 is 0. Derivative of x squared is 2x. We must put a dx dt with that. Right here, we're going to have to use our product rule. I'm going to just leave that 6 out as a coefficient. So I'm going to have x times the derivative of cosine, which is negative sine of theta, and we must put a d theta dt here. And then we, shouldn't close that parentheses yet, hold on. Plus, we'll have cosine of theta times the derivative of 6, or the derivative of x. I put the 6 out front, so we don't have to include that 6. So derivative of x is just dx dt, like this. So now we can just plug in the information that we know. So we've got 0 equals 2x, dx dt is what we're trying to find, minus 6 times negative x, sine of, they tell us that theta is pi over 3. We know d theta dt is 600 pi, plus cosine of pi over 3 times dx dt. And so we still need our x, so we've got to go back up here to our picture, and if we know that this is pi over 3, then we can do law of cosines to find x right here. So I'm going to go sort of over to the side here, and so we would have 7 squared equals 3 squared plus x squared minus 2 times 3 times x times cosine of pi over 3. So that's 49 equals 9 plus x squared minus, let's see, we could do 6x cosine pi over 3. You could subtract your 9 over here. 40 equals x squared minus 6x. I guess we could go ahead. Let's see if we could get. Let's go ahead and do 6 times cosine pi over 3. And 6. Let's see, I should know cosine of pi over 3 is 1/2. So that's going to be 3 right there. So 3x. And actually, let's move this 40 back over here. So we got 0 equals x squared minus 3x minus 40. And let's see. Yeah, this will factor. In the real world, this would probably never factor. And you'd have to use quadratic formula, but you could do a minus 8 and a plus 5. So you end up with x equals 8 and x equals negative 5. Because we're dealing with length here, we don't want to use that negative 5. We're going to use 8 instead. So, finally, let's go back up here, and for all of our x's, let's take those out, and let's put in that 8 that we just found. I think that's all of them there. And so we've got theta equals 16 dx dt minus 6 times, and then we're going to have, I'm just going to use the calculator for that. You got negative 8 sine of pi over 3 times 600 pi is going to be, I'm just going to decimals here. So negative 13,059.4 plus cosine of pi over 3 we just said was 1/2, so that's 1/2 dx dt. Alright, to solve this, we're going to distribute that negative 6. So we got 0 equals 16 dx dt minus 6 times that number is going to give us 7. My calculator's rounding weird, but that was actually a really long number. 356.1 something plus 3 dx dt. So if we combine here, we can put these together. So we got 19 dx dt. Combine those. I'm going to move this 78,356.1 to the other side. So we'll divide by 19. And we're going to get 4124.01 as our dx dt. And that is our, let's see what we're, these are inches per minute. So this would be 4,124.01 inches per minute. My calculator seems to be rounding in sort of a strange way. I feel like that it actually should be 0.007 if you round to 3 places. I don't know what my calculator's doing here. There, so that would be our answer for this problem. And you would expect this to be a pretty high number because that piston's going to be moving rather quickly. All right, let's look at example 3. A conical tank with a height of 10 feet and a diameter of 8 pi feet is being drained at a rate of 3 cubic feet per second. At what rate is the height of the water in the tank changing? So we've got a conical tank, so our tank is a cone. And it has a height of 10. And be really careful here. It tells you a diameter of 8 pi feet, which means that your radius, I wonder if it's supposed to have a pi. Well, we're just going to go. I'm going to take that pi out, just because it's going to make it difficult, more difficult. So a diameter of 8 feet. So that means your radius is only going to be 4 feet. So be careful with that. A lot of times they'll give us diameter and you might use it like a radius. At what rate is the height of the water in the tank changing? So you're draining water from the tank, and so the water level is going to drop. So what you're left with is a radius right here and a height of sort of that water that's in the cone. And so the radius is not 4 and the height is not 10, because both of those are going to change as the water drains out. So when we're talking about the water being drained at 3 cubic feet per second, that's your volume. So your volume formula here is going to be, volume formula for a cone is 1/3 pi r squared times the height. So this is our volume formula. We could go ahead and take the derivative of this. However, if we do that, then we would have 2 variables here, which means we would have a dr dt and a dh dt. And we don't have enough information to be able to do that. So what we want to do, this is saying at what rate is the height of the water changing. So we're looking for dh dt. So what we want to do is we want to rewrite this formula so that it's in terms of h and not the r. So let me show you what we can do here. This little cone right here, the water level, is going to be similar to the big cone. So that means we could set up a proportion with it. So if I say r over h from the small cone it's going to equal the radius over the height from the whole cone, which is 4 over 10. And so what we can do here is we can cross multiply. So we got 10r equals 4h, and we want to replace the r, so we're going to divide both sides by 10 here. So r is going to equal, I'm going to reduce here, 2h over 5, or you could do 0.5h, and 0.4h if you want there. So I can take this and plug it into my equation up here. And when I do that, my volume formula is now going to be 1/3 pi times 2/5 h squared times h. And so the good thing about this now is everything's in terms of h. So v equals 1, I'm going to actually write that as pi over 3 times 4 over 25 h squared times h. And we can put that together. We got 4 pi over 75, and then the h squared times the h is going to give us h to the 3rd power. So it actually gives us a really simple derivative to take here, because we just have this to the 3rd power. So if we take the derivative, on the left side we just have dv dt. On the right side, the 4 pi over 75 is a coefficient because pi is just a number. So we're just going to take the 3 and multiply it by 4 pi over 75, which is going to give us 12 pi over 75. That'll reduce, so we'll reduce that in a second. H squared, and then dh dt. And if we reduce there, which you don't necessarily have to do, but it'll make it a little smaller number to deal with, you'll get 4 pi over 25 h squared dh dt. And so we are looking for dh dt. We know that dv dt is 3 cubic feet per second, because that's the rate the water is being drained. And actually it's going to be a negative. So we've got -3 goes right here. We've got 4 pi over 25. We're looking for dh dt, so we're not going to replace it. We do need to know our h in this particular case. So let me look back. At what rate is the height of the water changing? And our answer for this, usually, I'm trying to look at, we need a height to plug in there, but we do not have that. So I think our answer to this is going to be still an equation. So we would just divide both sides by 4 pi over 25 h squared here. And dh dt would equal, over here, let's do this to the side, we've got -3, and we could sort of extend that out, that h squared would go in the top of that fraction. Dividing fractions is easy as pie. Flip the second and multiply. You got 25 over 4 pi h squared. So you would end up with -75 over 4 pi h squared. And so this would give you the rate at which the height is changing. You would have to know the height at whatever given time. This particular question did not give you the height. It gave you the height of the tank, but it didn't tell you what time you're looking at here. So if they told you, if they asked the question, at what rate is the height of the water in the tank changing when the height is 3 feet, then you would just plug 3 in for your H here. So that is what you would do for that. All right, so let's do our last one. So this one is still a cone problem. I think this is our last one. Yeah. Still a cone problem, very similar to the last problem. But this one does say how fast is the water level dropping when the water level is 6 feet and 2 feet. So we're going to plug numbers into this one. So we've got a cone again, and it has a height of 14 and a radius of 5. Water is being drained from the tank at a rate of 3 cubic feet per minute. So that is our dV dt is 3 cubic feet per minute. We want to know how fast is the water level dropping when the water level is 6 feet and then again at 2 feet. So we're going to do like we did on the last problem. We're going to start with our volume formula, which is going to be 1/3 pi r squared times height. And so when we're talking about what the water level is, we're talking about the height of that water level. So we're talking about this H right here. And as I said before, the height and the radius are both changing as the water level drops. So since we're talking about how fast the water level is dropping, that's our H, we need this to be in terms of H. So we're going to do like we did on the last problem and set up a proportion over here. So I'm going to say the radius over the height is going to equal the radius of the big cone is 5 and the height of the big cone is 14. So you can cross multiply and you'll have 14r equals 5h. We want to solve for r because we want to replace it, so we're only dealing with the h in this problem. So we've got r equals 5h over 14, and we can plug that in over here. So our volume is, I'm going to write this as pi over 3 times 5h over 14 squared times h. And so we've got pi over 3 times 25h squared over 14 squared is 196 times our h, which is in the numerator there. So we're going to have our volume formula finally here. Let's see, will anything reduce? I don't think so. That's going to give us 25 pi over 588, and it's fine to use your calculator on these. H cubed. Sometimes these will be given to you non-calculator, but they'll usually give you prettier numbers if they're going to do that. Let me just make sure that 25 over 588. That can't. No, I won't reduce. Okay. So now derivative. So over here on this side, we've got dV dt equals 25 pi over 588 times 3. Sorry, I'm not taking the derivative there. Got to multiply that by 3, which will give us 75 there in the numerator. H squared, and we have to put a dH dt over here. So this question actually asks us for the dH dt at 2 different times, once when the water level is 6 and the second whenever it's 2 feet. So our dV dt is -3 here because our water level is decreasing. And so we're going to have 75 pi over 588 times 6 dH dt. So let's just use our calculator there to find all of that stuff. So 75 pi over 588 times 6 is going to give us 2.4048 dH dt. We're going to divide by that number. And so if we do that, negative 3 divided by that number is going to give us negative 1.2477. And that would be in feet per, let's see, is this minute or seconds here? Minute. Feet per minute is your dH dt when t equals 6 feet. Now, if we look at our second part, we need to know the same thing whenever this is 2 feet. So we're going to go back and do what we just did. But we're going to use 2 feet instead. So we'll have negative 3 equals 75 pi over 588 times 2 dH dt, and that is going to give us 0.801427 dH dt, and we're going to divide both sides by that number there. So negative 3 divided by 0.801 is going to give us negative 3.743, and this is going to be feet per minute. That's your dH dt is going to equal when t equals 2 feet. And if you think about it, the height of that water should drop more slowly at first and then more quickly at the end. So this makes sense that we have a larger number here for whenever this is 2 feet than whenever it was 6 feet. So hopefully that will help some. I want you guys to try the problems that I have for homework today. I know that these can be very difficult. I hope to be back tomorrow. I hope that I will be feeling at least well enough to come in. So we will look over some of these tomorrow if we need to, or most of them if we need to tomorrow, because I know these can be a little bit difficult. So I hope that you guys have a good day, and let me know if you have any questions.